Good morning to those in the Americas. Good afternoon or good evening to those in Europe and in Africa, and good evening or good night to those in Asia or in the Pacific region. So today we are going to talk about solid oxide electrolysis for ammonia production. So we're going to talk about one of the first projects that's actually going to couple solid oxide electrolysis, so technology from Bloom Energy, to an existing ammonia production plant in Pryor, Oklahoma, operated by LSB Industries. Next slide, please, Andrea. So where does electrolysis-based ammonia production stand today? So if we go back a little bit in time, we see that in 2010, there were still 3 electrolysis-based ammonia plants operational. There was one plant operational in Egypt, operated by Kima. There was one plant operational by Sebo Chemicals in Kwekwe, Zimbabwe. And actually, the last existing ammonia plant based on electrolysis is located in Peru. And we will also discuss that plant in the webinar of next month. So what you actually see is that the Kima plant has shut down in 2019, and the plant operated by Sebo Chemicals has shut down in 2015. So if you look at the graph right here, so what you see is that over the past decade, electrolysis-based ammonia production has basically decreased just from almost 300 megawatts to only like 30 megawatts still operational. However, in recent years, the first small-scale projects based on renewable electricity, so instead of just hydropower in the past, which is very stable, also some projects have started based on solar power and wind electricity, which are intermittent. And the interesting thing that we see in the recent years, so in 2022 and 2023, is a diversification of electrolysis technologies being used to produce ammonia. Whereas first it was just alkaline electrolysis being used, we also see multiple megawatt projects of PEM electrolysis. So if you see the projects that the added capacity from, let's say, 2020 to 2023, that's about half alkaline electrolysis, half PEM electrolysis. And by the end of 2023, what we actually expect is a total ammonia production from electrolysis-based ammonia production, that the total capacity will be about 183 kilotons per annum. And that equates to about 0.1% of the global ammonia demand. So it really means that if we are going to use ammonia as a zero carbon fuel or as a hydrogen carrier, we really need to scale up. Now we are talking about alkaline electrolysis and PEM electrolysis. However, there are also novel electrolysis technologies. So first of all, there is solid oxide electrolysis, and secondly, anion exchange membranes are also used for electrolysis. But today we're going to focus on solid oxide electrolysis, because Bloom Energy is going to provide 10 megawatts of solid oxide electrolyzers to the facility of LSB Industries in Oklahoma. Next slide, please. And the interesting thing here is actually that solid oxide electrolysis is always this technology that is under development, but Bloom Energy actually took it to the next step last year when they tested their solid oxide electrolysis technology together with nuclear reactors at Idaho National Lab, and it really showed that this was very stable for about 500 hours, and it was way more efficient than other electrolysis technologies. So they really showed that solid oxide electrolysis is there in the future. And now I would actually like to move on to our first speaker. So that is Rick Beuttel from Bloom Energy, who will discuss the solid oxide technology that Bloom Energy is developing. So Rick, the floor is yours.
Thank you, Kevin, and I will join you in wishing good morning, good afternoon, and good evening to the audience. It's a pleasure to be here today, along with Jakob from LSB, to talk about Bloom's technology and, of course, the very exciting work that LSB is doing, leading the way for clean ammonia production here in the United States. I'm Rick Beuttel. I look after the hydrogen business here at Bloom. I've been here at Bloom for a little over a year now. Prior to that, I spent a little over 30 years at Air Products, where I was running large projects business development for the Americas. So very familiar and have a long history of developing clean hydrogen projects, gray hydrogen projects, and more recently, clean ammonia and other derivatives like renewable diesel. Again, it's a pleasure to be here today. So why don't we dive right into it? If you could advance the slide kindly, Andrea. Thank you. For those of you who aren't aware about Bloom, let me just touch on a few figures here. So Bloom was founded based upon foundational work that our CEO and chairman, Dr. K.R. Sridhar, was doing for the NASA Mars program in the late 1990s. And basically, K.R. was tasked on behalf of NASA to develop an electrolysis technology that could go on the Mars mission and electrolyze the Martian atmosphere, principally seeking oxygen to be used, of course, to sustain human life and also as a fuel. When the Mars program was canceled due to budget constraints at NASA, KR did probably what every bright young PhD did at the time with his work. He moved his family to Silicon Valley and started a company, which ultimately became Bloom. The world, of course, was not ready for clean hydrogen the way we are now. So KR took that same solid oxide platform, and you'll hear me use that word a lot, platform, and as I see it, ran it backwards. And when you take the electrolyzer technology and you run it backwards, it's a very efficient high temperature fuel cell. So Bloom has been built around a fuel cell business. We have roughly 1 gigawatt of installed capacity of fuel cells. People know that fuel cells are rated on power out. Electrolyzers are rated on power in. The conversion's a little over 2 to 1. So we've built, from a stack standpoint, over 2 gigawatts of electrolysis equivalent stacks. We have a very large backlog. We've spent a lot of money in research and development. And one of the very interesting things about solid oxide is there is a bit of a Moore's law component to how we build the stacks and how we build the units. So you see that over the last 15 years of building a gigawatt of stacks, we've achieved actually a very enviable annual learning rate of 10 to 12% per year, even during COVID. So even with all the supply chain constraints in COVID, we admittedly did not deliver 12% in the last 2 years, but very close to that. So we're very excited about the future of our solid oxide platform, and have recently, in May of last year, opened up our new GW-scale factory here in Fremont, California, very close to our headquarters in San Jose, actually close to Elon Musk's Gigafactory that builds Teslas, is just down the street from us. And that facility can build 1 gigawatt per year of fuel cells or over 2 gigawatts per year of electrolysis. So while other companies are talking about and getting ready for and planning their gigafactories, ours is finished and has been operational since last May. We actually hosted our investor day there. Next slide, please, Andrea. Thank you. So what we're here to talk about today, maybe getting a little bit more granular now that the background's out of the way, of course, is green ammonia. And what the LSB project is, of course, is replacing and backing out some gray hydrogen, and Jakob will go into that in a lot more detail, and replacing it with green hydrogen from renewable power feeding an electrolyzer. What is particularly compelling about high temperature solid oxide is the ability, when you bring the water molecule into the electrolyzer, because the electrolyzer operates at approximately 700 degrees C, if we can have that feed be low-grade steam, 150 degrees steam C or thereabouts, it supercharges the efficiency even further. Kevin very kindly showed an excerpt from the press release from INL, but with steam integration, we can deliver hydrogen from the electrolyzer at a specific power well under 40 kilowatt hours per kilogram. We'll get into that a little bit more later. But I think everyone else on this call clearly knows the rest of the process, classic Haber and Bosch, ammonia synthesis, a big loop compressor, round and round it goes. You add in nitrogen and hydrogen and you pull ammonia out for export. And really, this is Jakob's thunder, so we'll let him talk to that. Next slide, please. High-level comparison of the two predominant existing technologies, which Kevin spoke of course, alkaline is a very, very mature, established, proven technology, relatively low CapEx cost on an installed basis. However, and you'll see in a moment, it does cast a long shadow in terms of not having the world's best efficiency. And we've chosen for this comparison 54, obviously, depending upon the technology licensor and how they're precisely doing the alkaline, that number is somewhere in the middle 50s. PEM, newer kid on the block, better efficiency, slightly higher cost, for the electrolyzer itself. And one concern with PEM, of course, is the inclusion of platinum and iridium in the package. So that may gate the ability to remove cost from the technology in the future. Finally, our technology is on the extreme right, solid oxide electrolysis, sort of next generation electrolysis technology, although in our case, it is literally built on the back of, a gigawatt of installed fuel cells and a manufacturing line that is lined out, et cetera. The efficiency, as I mentioned, under 40 kilowatt hours per kilogram with steam integration, which is applicable for ammonia. If there's an opportunity which does not have steam available, so not tied to a high temperature synthesis process of some sort, say hydrogen for mobility or liquefaction, and we're just fed water as a liquid like we drink, the spec power goes up to 45 kilowatt hours per kilogram. So still good, but not supercharged and world beating like a number under 40. Next slide, please, Andrea. This is our LCOH, levelized cost of hydrogen analysis. For the purpose of this discussion, we've excluded any sort of production tax credits like one might see for the Inflation Reduction Act here in the US, or equivalents that either exist or will exist in the future in other economies. What I always take from this is that the cost of the electricity itself is roughly 70 to 75% of the cost of resultant hydrogen. So the most efficient device is always going to win. This analysis has been normalized to 30 bar hydrogen, so the technologies which require compression, alkaline and solid oxide, have had the cost of CapEx and OpEx for compression added in. We have made some assumptions based upon publicly available studies over the cost and degradation of each of the technologies. Of course, we know ours very well. And then you see at different costs of electricity, of course, the higher the cost of electricity, the more marked the spread is in LCOH. So there are probably going to be some questions about this, but what I would say is, we picked this and we're very holistic about the assumptions, not overly aggressive in any case, and ran this at an 8% return on capital. So it just shows the indication that efficiency really carries the day from an LCOH perspective. Next slide, please, Andrea. Here's a little photo of our installation at Idaho National Lab. The press release was timed when we hit 500 hours. The unit has run continuously since then, and we are now well over 3,000 hours of operation. I think two comments. One is that from a standard performance perspective, so that's sort of without the engineers and the lab coats and the PhD hovering over it, tweaking the dials. It's probably a bit of an eye chart to read, but you see the figure there is 39.19 kilowatt hours per kilogram of electricity. And then from a peak performance standpoint, which is optimized, and again, the people with the lab coats monitoring it and tweaking it, 37.7 kilowatt hours per kilogram. What excites me about that is that with what we're willing to guarantee today, the standard performance, we don't view that as the end. We view that there is a lot more efficiency. There's a lot more cost we can take out of this platform, and I think this test illustrates that. Next slide, please. I think we talked about this already, Kevin. I was not aware you were going to excerpt it, so in the interest of time, why don't we skip this? High points. So we talked about market-leading efficiency, results in the lowest LCOH and the lowest carbon footprint hydrogen. It's an ideal solution for any exothermic synthesis process. Of course, we're here and very excited to talk about ammonia. Actually, ammonia is a little bit of the reason I left Air Products to come to Bloom, because I recognize the value in being able to integrate this next generation technology with ammonia synthesis. But the same point applies for other processes, whether that's renewable diesel, sustainable aviation fuel, methanol. These processes generally are all exothermic, require large volumes of hydrogen, and produce an end product which either today or in the future will be traded on its carbon intensity. So we're very excited about it. People often ask about stack life. What I will say is, in a fuel cell, our stacks last 5 to 6 years. In an electrolyzer, it's the same material set, the same cells, same. But there's no sulfur in the feed into an electrolyzer like there is in natural gas coming in. That's a poison to the catalyst. There's no C2s, C3s, C4s. That's a poison to the stack. And there is also a differential. The electrolyzer runs at about 100 degrees C lower temperature. So 5+ year life in an electrolyzer mode, we're very comfortable with based upon our gigawatt of operating experience. I would further point out that with solid oxide, unlike some of the other technologies, in the first 5 years, you do not see any degradation in capacity or efficiency. After that 5-year mark, you pass over what's called thermal neutral, and I'm happy to follow up with anyone and go through the chemistry and why that is. But after 5 years, we do start to see a bit of degradation, 3 to 4% per year. But this is a differentiator for solid oxide. As I mentioned, we have a gigascale manufacturing facility in place. The resiliency is very much inherent in the design. It is a large number of modules all operating in parallel. So when it comes time to do that stack replacement or any other maintenance, you can literally take small sections of the plant down at a time, which yields hydrogen availability from the electrolyzer. We believe, and again, based upon our fuel cell experience and the several years of work we've been doing on electrolyzer demonstrations, greater than 99%. People often ask how well this technology pairs with renewable feeds. What I would say is we go from 5% to nameplate, 100%, up or down in less than 10 minutes. So it's not instantaneous like PEM, but it is better than alkaline. And candidly, I've never had a renewable power developer or an ammonia developer say that, you know, this isn't good enough. And then our business model is as a sale of equipment. So we're not like where I came from at Air Products, where they want to sell you hydrogen. We're in the business of selling equipment and then supporting that equipment for the life of the investment. Next slide, please. I think I only have one more. There you go. So let me give the keys to Jakob. Take it away, my friend.
Great. Happy to be here sharing the stage with Rick in this very unique and technologically advanced project. I'm Jakob Krummenacher. I lead clean energy for LSB Industries. Andrea, next slide, please. LSB at a glance, we are the 5th largest ammonia producer or nitrogen producer in the United States. We own and operate 3 facilities, mainly in the South, Oklahoma, Arkansas, and Alabama. Most of the ammonia that we make, about 2/3 of it gets upgraded into downstream products, nitric acid, AN, UAN, urea. But about 1/3 of it, we sell it directly into the market. We've been a company since 1968, and this year is actually our 50th-year anniversary of being a public company. Looking at the chart on the bottom left here is something that's unique about LSB is most of our sales are a 50-50 split between industrial and ag consumer, or industrial mining versus ag. Most nitrogen producers that you see in this table, or in general, they typically tend to sell about 80 to 85% of the volume into the ag market. So we have a much higher industrial exposure than our competitors. Next slide, please. Here is our initiative for growth going forward for the company. And as you can see here, very important piece for us is to become greener, to reduce our carbon footprint. And for that, we're looking both at blue ammonia and a green ammonia. We have a couple of those projects ongoing, one blue in Arkansas and one green, which is the one we're going to be discussing further, that is happening in Pryor, Oklahoma. We're also looking to expand new capacity and potentially other geographic locations as well. Andrea, next slide. Thank you. So here is the project that we're doing in Pryor, Oklahoma. Why Pryor, Oklahoma? That's because Oklahoma, out of our 3 locations, is the nearest or the closest to renewable power sources, solar and wind in particular. So it should be, the closer you are to the source of power, the lower the price that you could get, right? So in a nutshell, this is what we're doing. The gray boxes and the black lines at our existing ammonia plant. It makes 230,000 tons of ammonia a year. We're going to take a portion of the hydrogen made from natural gas, and we're going to decline that, reduce it, and then going to replace it with the green hydrogen coming from the electrolyzers. Our intention was to test the 2 technologies, alkaline versus solid oxide. So an opportunity for our engineers to learn both of those. And as you can see here on the right, there is the Bloom electrolyzer, which we're planning on a 10 megawatt unit, and then a 20 megawatt alkaline unit, which we still don't know the supplier of that unit, but here's a couple of options that you can have from ThyssenKrupp and Nel Hydrogen. This project, because of the reduction of natural gas consumption, is going to improve the carbon footprint of the facility by reducing it about 36,000 metric tons of CO2 annually. So it is a small project, but it's mainly a proof of concept that we're trying to do. We're expecting to secure government incentive in the form of tax credits. Today, you can do the IRA or Inflation Reduction Act. For the production of clean hydrogen, this project could qualify for the $3 per kilogram of hydrogen. We're also involved with the hydrogen hubs. You know, the government is going to deploy funds to incentivize projects for the production of clean hydrogen or clean ammonia. And we're expecting to participate in that as well. And I believe that's the last slide that I have.
Thank you so much, Jacob. And indeed, it's very interesting to see that a few years ago, solid oxide electrolysis was still a technology, you know, that you read about in the academic literature on the kilowatt scale. And now we actually see a project where in 2024, 10 megawatt is going to be installed. And I want to ask you, Rick, right now we see like multiple projects of PEM electrolyzers and alkaline electrolyzers being developed in the tens of megawatts range. When would we actually be able to see like a 1 gigawatt scale solid oxide electrolysis based ammonia plant? Would that be limited by, let's say, capacity of your production plant, or would that just be a demand side question?
So Kevin, a couple of comments there. So the LSB project represents one of several deployments at a 10 megawatt scale. I'm not at liberty to discuss the other ones because of confidentiality. But what I would say to build on that is our go-to-market with this technology is at a 10 megawatt block size and a 25 megawatt block size. And to make it simple, right, a 25 megawatt block has 2.5 times the amount of stacks, of course, as a 10 megawatt block. We are engaged, as probably all the electrolysis suppliers are, in pursuing a number of large projects of this type around the world. I think we see an enthusiastic reception, in particular amongst the ammonia community, recognizing the value of efficiency, because you can either take that as more hydrogen and more ammonia for a given amount of renewable, or you can buy less electrolyzers and, you know, buy less renewable power, contract for less renewable power, and save money that way. We are scaled up, we are capacitized. Finally, what I would say is our Fremont facility, which opened the middle of last year, in a very, and I'll say this tongue-in-cheek, easy place to build anything and do business, that being Northern California. We completed construction, move-in, and startup of that facility in 12 to 14 months. And I think our next facility will not be in California. It'll be in some place probably a little bit easier to do business quickly. And our capital plan says we will build a facility like that roughly every 2 years. So from a solid oxide standpoint, our order book is open. We have a lot of interest, and we are very happy to engage on a scale of tens of megawatts, hundreds of megawatts, or a gigawatt, and we will build them. Thank you for the question.
Thanks so much. And Jacob, maybe to add on top of that, so Rick already mentioned efficiency and some other factors that might affect it. What were some of the other key drivers for LSB to say, yes, we want a 10 megawatt electrolyzer at our facility? Are there any additional benefits that you can think about?
Yeah, I mean, electrolyzers are expensive, right? Compared with conventional ammonia production, but there are incentives from the government, incentives from other governments that are trying to subsidize ammonia usage, like Japan, for example, and that helps close the gap. But when you're comparing the two technologies, for example, in our project in particular, if you say secure renewable power of $40 a megawatt, on a alkaline electrolyzer, that represents about $2.60 per kilogram of hydrogen production on electricity alone. In a solid oxide technology, you're looking at about $1.80, so a significant reduction. Now, those two numbers are still a bit high compared to the nat gas, because $1.80 hydrogen is about $9.50 gas, and gas is trading at $3 today, versus $14 for the alkaline unit. We're hoping that in the future, and that's the main reason why we're doing this, that in the future, not only the incentives that are in place are going to help bridge that gap, but also the potential for a carbon tax or a carbon cap and trade with border adjustment. Those things will help narrow the gap to conventional ammonia. Further down the road, there will be industrial demand, industrial users. For example, ammonia is used in small quantities in cleaning agents or household cleaners. So a 10 cents increase on a bottle of a cleaning agent would not prevent anybody from buying the product, especially if it has a label on it that says made with 90% lower carbon emissions. That 10 cents in that bottle can represent thousands of dollars per ton in the supply chain. And that's how, you know, we're gonna see the future for that. And then further down the road, which what Rick mentioned, is that scientists and engineers will continue to work on the efficiency and lowering the capex, and eventually this unit become more cost competitive, similar to what happened to the solar panel industry in the past.
Thank you so much, Jacob. And you're totally right. And what I sense a bit is that you try to be early to the game, also to make sure that once this scales up and maybe ammonia will be traded even more broadly around the world for new sectors like the maritime sector, power generation, or maybe for hydrogen generation, for instance, in the north of Europe, then you already have some operational experience. I actually want to move to a little bit of another topic where you have this 10 megawatt of electrolysis from solid oxide being announced, and then you have like 20 megawatt of PEM or alkaline electrolysis, like at least low temperature electrolysis being announced. And in total, that would be like something like 30 kilotons per annum in that ballpark range. And that would be like maybe max 10% around that ballpark figure of your total ammonia capacity. So is there a reason why you went for this 10% and not for like 2 or 20, 30? What are the reasonings behind that?
So we did a feasibility study to tell us exactly oh, sorry, you guys were frozen for a moment. So yeah, we did a feasibility study to tell us just that, right? And as you lower the operating rate in an ammonia plant, a conventional ammonia plant, your cost per ton goes up, right? That's you know, understandable. So there is a sweet spot of how much your cost can increase versus how much you know, the benefit of the green hydrogen, and that was determined at this rate level. So ultimately, you know, in the future, you could envision if electrolyzer become cost effective, you could envision a way to completely, you know, get away of the SMR and then replace all that with hydrogen and electrolysis and an air separation unit as well. That could be running a way of running the ammonia loop that way. So
would you then think about revamping like an existing SMR system, combine that maybe with electrolyzers, or would you at some point say, okay, let's rethink the design of an ammonia plant, maybe even with like a combination of a solid oxide electrolyzer and an ATR?
I think all of the above. I think you know, you need ATR technology, you need carbon capture sequestration, If you make ammonia, you're going to be in an exothermic process. You're going to have excess heat. You can turn that into steam. You can feed it into electrolyzers like the solid oxide units, and then you can generate hydrogen from that water. And that helps, green up their operations in general. But I think that today, large-scale electrolyzer ammonia plants are obviously too costly, but that's something that might change down the road.
Rick, could you also comment on the combination of your electrolysis technology, both being a hydrogen production plant and an oxygen production plant, for maybe a combination with fossil-based hydrogen production?
Sure. So, Kevin, like any electrolysis process, the byproduct is oxygen. And, for a large enough project, for a large enough opportunity, it would be economical to recover that, whether as pure oxygen or enriched air. I don't think, having done some ATR projects in my prior life, generally speaking, the way you make that economical versus hydrogen from an SMR is scale. So I personally would look at, if you were going to twin this electrolysis with autothermal reforming for ammonia, you could take the benefit, to Jacob's point, of heat from the ammonia loop, right? We all know autothermal reforming is also exothermic, so there would be some steam available for that. Pair hydrogen from an electrolysis, make a blend of blue and green. So maybe we'll come up with a new color. We'll call it teal or something like that. And then the oxygen from the electrolysis could pair with some additional oxygen from an ASU, an air separation plant, which needs to be there anyway, right, for nitrogen for the syn loop.
Yeah, totally right about it. And even when you're discussing your technology and comparing the technologies based on a 30 bar output hydrogen, I would even consider that an air separation unit would produce nitrogen at up to 10 bars. You could actually combine your hydrogen production with your nitrogen production, and maybe even make the compression a lot more cost effective, because normally you would never separately compress your hydrogen, because it's probably one of the most expensive molecules to compress. I want to follow up a little bit on the stability, because you mentioned this 5 to 6 years, whereas in academia, like in all these papers over the past 5 years that I've read, people say, okay, after 2 years, after 3 years, it has been degraded a lot. So what are kind of the developments from your side that have made that the stack lifetime has improved so much?
Kevin, and I read a lot of those same papers, as a long time aficionado of hydrogen in my prior life. And I thought the same thing, to be candid with you. But then I came to Bloom, and I interviewed, and I talked to the operations people, and I went to the factory. And what occurred to me is what has made Bloom successful is a bit of the Silicon Valley culture merged with an energy industry culture. And the part of the Silicon Valley culture is sort of fail fast and learn from the failures. So as I mentioned, Bloom has been building solid oxide fuel cells for 15 years commercially, and doing research before that. If you looked at the lifetimes of our solid oxide fuel cells 15 years ago, it was a year, 18 months. And over time, we've learned how to manufacture them so that they're less, variables in terms of deployment. We've learned how to support them. We've learned how to run it as a system. And most importantly, I think we've learned the best care and feeding to ensure a long life. And I would say that in my view, I had not thought any entity was this far along in the solid oxide journey, because as a hydrogen person, it never even really occurred to me to look at the natural gas fuel cell space. But when I saw what Bloom has done, really this technology is much, much, much further along than any of the literature would have you believe, as expressed by Bloom. And I think that solid oxide is a bit, I'll use the word sexy. Hopefully I don't offend anyone by saying that word. And there are many other entities getting into the space. I think we welcome that, because the more people that are out there talking about it and talking about the benefits in terms of efficiency and LCOH, the better it's going to be for all of us. And, we welcome competition. But I think we have a pretty big head start because of the fuel cell business. And as I mentioned, electrolysis is actually technically a much easier service than how we've cut our teeth and, got scars on our hands from building fuel cells for a decade and a half.
Yes,
I
and
think that I just
Go
want to
ahead,
add that I think that part of the reason that it was not known is because it's a NASA kind of technology, right? It's all secretive until it gets to be deployed outside in the real world. Then nobody knows how advanced it was until now.
Yes, and I think also it is not just Bloom Energy saying this, and because also in Europe, like Topsoe also announced that they will build a multi-hundred megawatt scale factory. So if multiple electrolyzer manufacturers in the solid oxide space claim to be able to do this, and if we get this operational experience from, for instance, the Pryor plant in Oklahoma, that will really help us along the pathway. Jakob, once again going back to this oxygen byproduct, is there any current process? Is there like any downstream application where you could use this oxygen or any other products that you make?
Yeah, we're looking at that very, very carefully on what to do with the oxygen or oxygen-enriched air. And we haven't identified any direct uses other than using it into the furnace of the SMR. So if you combine oxygenated air or high concentration of oxygen with natural gas, then you can potentially reduce the amount of gas to generate the same level of heat, because now you don't have that much nitrogen to heat up. So that could be another efficiency factor that can lower the carbon footprint of the facility, but if we can reroute that oxygen.
Thank you so much, and I think indeed it's very good to see indeed that you could use this oxygen for other places. Otherwise, it's a bit of a loss. And I was even thinking maybe you could even use it for instance, nitric acid production or any other processes, which maybe today are more geared towards air as a co-feed for ammonia. But of course, that remains to be seen, and it's more of a thing that people look at in the future. And Rick, you mentioned this flexibility of this electrolyzer is quite strong, that you can go from 5% to 100% in like 5 minutes. What would happen if you have like a cold standby, or would you always recommend to have like a hot standby in this kind of applications?
Kevin, it's a great question. And, you know, I saw some questions to this effect in the Q&A. I was cheating and just looked down at those. And I think to ensure long life of the stacks, you know, one thing we've learned over these, you know, literally hundreds of billions of cell operating hours is that the secret is to keep the stacks hot. So when the renewable resource is not available to support ammonia synthesis, right? And of course, you want to look at a whole system, especially on one of these very, very large, you know, grassroots green projects. We still do require what we call parking power or keep hot power. Right now, we're estimating it at 5% of nameplate power, just to keep the stack at temperature, so that when the renewable resource becomes available, instantly you're back to production. That's the first reason. The second reason, of course, is that it's a high temperature, it's a ceramic substrate with literally a cathode and an anode ink set on either side containing the metals. And you want to keep that hot to ensure this long life of the investment. So no, we really do need to keep the stacks hot.
And when you're talking about these ramp speeds, is there like a certain frequency or like a recommended, you know, like ramping per day or something like that you cannot do it too often, or is it like once per day, or is it like once per hour that you can do this?
No, I think as long as you keep it hot when you're not operational, you know, and the economics wouldn't make sense, and you also wouldn't want to, you know, move the SIN loop around, I don't think, that much. But no, I mean, the technology is tolerant of moving it around. And, you know, 5 years ago, 10 years ago, we wouldn't have said that at Bloom. But, you know, we have been on this learning journey and this innovation journey, and have learned some things. And again, electrolysis is a bit of a different service than fuel cell. So it offers a different operating profile. What I would not want people to leave this call thinking is, oh, well, then you can do that with the fuel cells. And, you know, the reaction dynamics of a fuel cell is different enough than that of an electrolyzer, that, you know, not necessarily the case for an SOFC, a solid oxide fuel cell.
Thank you for that. And maybe to follow up a bit on the flexibility side. So Jakob, let's assume that you would integrate this solid oxide electrolyzer or even some other electrolysis technologies maybe. To what point could you actually like go with making your facility green, and what kind of limitations would you expect in terms of flexibility for your other equipment that you have in the process?
Yeah, I mean, we're open to make it as much green of a facility as it can be, provided that the economics for doing that add up, right? So it's a matter of time, I think, that for the incentives to roll through, for the premium on the price of low carbon ammonia to develop, and also the technology for the solid oxide to continue to lower in their costs. So once those things happen, then we'll be definitely open to doing something along those lines. But in the meantime, we have to deal with, you know, how do we control these? How can we build it? How can we access what the government is providing? Because the government is just trying to do that. It's trying to bridge that gap between today and the future when things will become economically competitive, right?
Yes, for sure. And that's also why they're incentivizing this quite strongly, especially in the US, and probably some other countries and continents are very likely to follow in a similar direction.
Yeah.
And I was also wondering, you have like these different technologies. Is there also like a mix and match approach that you think about, that maybe you have some baseload technology that you want to use, whereas another technology is more for ramping up and ramping down electricity production? Is that a consideration as well? Let's say you have a solid oxide being more baseload-ish, whereas say like a PEM electrolyzer is more for peak shaving, for instance.
That could be. I mean, the one thing that you have to keep in mind as you combine technologies, and we went through this in our feasibility study, is that the inputs are not the same, right? In an alkaline unit, you need high purity water, so reverse osmosis. In a solid oxide unit, you need steam. So, you know, you need to make sure that depends on what you have available and what you need to build in terms of cost. But the more of the different technologies that you have on one side, the more of these issues that you're going to be having, right? Because obviously you have only solid oxide and you're only worrying about steam and power. If you have alkaline, then you're only worried about clean water and power. Yes, but that's a good point. I do think, though, that if you're looking at renewable power and the intermittency of solar and wind, I think there is a need for nuclear, for example, which is a carbon-free base load 24/7 type of power. Hydro could do that, but I think in the US we're tapped out of all of our hydro opportunities, so it cannot be further increased. But that would be great if you can have a source of power that is continuous and can serve as a base load and is carbon-free. Then you know you're free to use any electrolyzer you can, right?
Thank you for that.
Kevin, we're active on several large opportunities right now, where I think some of it is just the customer trying to optimize the match of, as you say, base loading solid oxide for the first tranche and sizing that to match the amount of steam that just sort of naturally comes off the syn loop. And then putting like a bit of a layer cake on top of that of a secondary technology that's maybe a bit faster responding. And so I'm talking about PEM here, and taking the swings in PEM, which is a little bit less efficient, but also responds, you know, more instantaneously. And it does raise the challenge that these new large mega scale green opportunities that are in different parts of the world, there's not a cookie cutter answer. It really depends quite a bit on the pattern of the renewable resource feeding it. And I think Jacob's exactly right. We're tapped out on hydro here in the US. We have nuclear. In other parts of the world, you know, there is hydro available. And if you can get a base load of some of that, and you can pair that with the wind, as I mentioned earlier, you really also need to think about not just the electrolyzer. Many people on this call know syn loops a lot better than I do, right? And you've got a tens of megawatts synthesis loop compressor that you don't want to be jerking up and down as well. So you really have to take a holistic approach. And I think the answer is bespoke to the opportunity. And I think that's where smart EPCs and smart owners are going to determine the right fit for each opportunity. And that's where you maximize value.
And thank you for that, Rick, especially for the electrolyzer part. It's very clear there are different technologies, have their different pros and cons. But I even see on the ammonia synthesis side that there are quite some different approaches to do things. You could have hydrogen storage, quite significant, just to make sure that there is always some hydrogen inflow there. Whereas other companies are also claiming that they kind of want to get rid of hydrogen storage altogether, or at least like almost get rid of that, and just keep the loop hot, maybe with electric heating and some other measures. So it's just not only the electrolyzer that people are still thinking about, and you see also this match and play with the synthesis loop indeed. I was also wondering more on a different, let's change the topic again. It's a different topic is the materials to use in solid oxide materials, because for PEM that of course is an issue to tackle and to make sure that the precious metals are recycled. Is there something similar for solid oxide electrolyzers, or is this less of a problem?
Much less of a problem. So, a solid oxide cell is made up of an electrolyte, which is a ceramic material, with a cathode layer painted on one side and anode layer painted on the other side. It is for our American listeners or viewers, it's sort of like Colonel Sanders' secret recipe, right? I mean, I'm told there's only 2 or 3 people at Bloom that know the entire material set. But what I will say is all of the materials that go into those metals are at least triple sourced. None of the sources are in Russia, China, or the Ukraine. There's no, rare earth metals. There's no platinum or iridium, right? So no PGMs. And we actually do, for several reasons, recycle when it comes time to change the stacks out. So KR's mentality from day one here at Bloom is it is just good to be a responsible steward of the planet's resources, that when the stack is done at end of life, it comes back to one of our facilities and we reclaim about 97% by mass of the assembly that comes back. So that's one reason. I think the second reason we do that, just being a bit more pragmatic, is we also don't want, the cast-offs from our technology ending up at a dump or a landfill or someplace like that, where someone else could maybe get access to the technology and go reverse engineer the material set and figure out why we can make our stacks last longer than other people. So we do recycle and recover. Yes, sir.
That's very good to hear, because sustainability is, of course, part of this journey, and it's also why we are doing it. And Jakob, from a sustainability perspective, this energy efficiency gain that you have for the hydrogen production versus, for instance, alkaline electrolysis and PEM electrolysis, does that make a big impact on the overall carbon footprint that you would expect for your ammonia production?
So the project is small compared to the size of the facility, and it's not different than many of the other green ammonia plants that are being built today or planned. They're going to be add-ons to large ammonia plants, right? So the impact overall on the site is small. Ours is going to be about 36,000 tons of CO2 reduction a year. However, I might say that the way that we thought about going into the project initially, and we still haven't decided yet, but the 10 megawatt solid oxide and a 20 megawatt alkaline unit makes the same amount of hydrogen that you had at 24 or 25 megawatt of solid oxide. So, one of the questions is that additional 5 megawatt, how much cost is that? And $40 a megawatt is significant, right? If you perpetuity over time, 10 to 20 years of the life of the project, then it can make a difference on how you think about the project. We're very excited to test these technologies, the solid oxide, and Bloom will help us. They will operate the electrolyzer for us initially, and then we'll get to learn how to run them, how efficient they are, how they behave on a real world setting of ammonia production. And then at some point we can decide whether we'll go, set up an alkaline unit next door or another solid oxide unit next door, next to it. Reason being too is that the alkaline units are on a back order of about 2-year timeline. So, they're going to be not happening at the same time because of that very same reason.
It's kind of interesting how an emerging technology can be faster to deploy to your site than a technology that has been around for a century. Also wondering, just one topic I want to go into before we close up the hour as well is safety. So in the studies that you have done so far, Jakob, do you see similar safety standards for solid oxide technology, or are there different concerns versus, for instance, alkaline electrolysis or PEM electrolysis? Is it significant on the overall plant layout?
There is very little difference in the safety front on the regardless of the technology that you use, and the main concern is hydrogen, right? And hydrogen storage in particular, which is an advantage in ammonia production, because if you are going to make hydrogen, you're going to use it right away, right? There's no storage needed. We're going to have some temporary storage as is required for the initial startup operations, but then once you do that, then it's not needed anymore. You do need to compress the hydrogen, because an ammonia plant where the hydrogen comes in operates at about 400 psi, and most electrolyzers make it at 0 or a few psi of pressure. So you do need compression, and as you mentioned earlier, hydrogen compression is expensive. So I think the compressors that we have planned for the project, if it goes in at a 30 megawatt, it will be about 4 megawatts of hydrogen compression. So it's a lot of power.
Yeah, I can imagine that indeed the compression is a contentious issue, and also it can also be a long lead time item. Last month I was actually talking about a project in Egypt, and basically the choice was made for PEM electrolysis, and one of the reasons to not go for alkaline electrolysis was because it would require a hydrogen compressor, which would not be required for the PEM electrolyzer in their case. So Rick, could you also talk about safety, and you also mentioned something about maintenance, that you could do this modular. So how should I see this?
So two things there. One, I think from a safety standpoint, we've done a very exhaustive safety review. We're well cognizant of the issues around hydrogen. We've brought in, third-party agencies as well. And besides myself, several other people have joined Bloom from the industrial gas community with a hydrogen-specific expertise. So we're very confident in our production of, to Jacob's point, low pressure, saturated hydrogen at the exit of our device. And then I think we would work with the customer's chosen EPC or engineering organization to ensure from a systematic standpoint that all the interconnections, whether it's steam and electricity in or hydrogen and oxygen out, are handled safely, are controlled properly, so that there's no introduction of a dynamic into the system which would create an issue in the hydrogen production of the system. And then I think finally, just to touch on modularity for a moment, I think you do plan on making the slides available to everyone, Kevin. One of the very early slides on Bloom showed sort of a field of the silver kind of Bloom boxes, is what the world calls them. That is a 30 megawatt utility scale fuel cell installation in Korea, and I'm a pretty visual person. I always find that helpful to show people what a big installation looks like. From a hydrogen standpoint, you can literally isolate those in blocks of 4 for maintenance. So if you consider there's, and I'm just going to make up numbers here, 200 modules, you can isolate them in blocks of 4 for maintenance. So from a percentage standpoint, that's 1 or 2%, while keeping the rest of the facility online and fully operational.
Thank you for that, Rick. And now we are about 5 minutes to the hour mark. So right now I would like to focus a little bit on forward-looking statements. I know that companies are often quite hesitant, but I would like to quantify success. So Jakob, if you think about projects at Pryor, Oklahoma, but also about other projects. So if you look 5 years from now, maybe 10 years from now, what has defined success in this decarbonization path that you've taken at LSB?
Yeah, so at LSB, we'll look, obviously, you can measure your carbon footprint. So anything that you can do towards that front will be a success in terms of greening the company operations. But more specifically, in terms of electrolysis, a success will be having a successful project ongoing, potential expansion capabilities at some point in time over the next 5 years. And more importantly, we'll be very keen to look at new standalone ammonia production plants that combine both the blue with the carbon capture and sequestration, and then utilize that excess heat from the ammonia and the ATR so that you can make hydrogen via electrolysis, and that, you know, further enhancing the capabilities of green products, or a combination of blue and green, or turquoise, if you will.
Thank you so much. And indeed, the integration is also a very interesting concept here. Rick, so if you look from Bloom's perspective, and then maybe a little bit focused on the ammonia production side, so what does define success for you in the coming 5 to 10 years? What are we talking about?
So our focus from an early day here in commercializing the electrolyzer has been really focused on efficiency and delivering our efficiency, because that casts the longest shadow in terms of LCOH. That said, obviously CapEx is important, obviously OpEx is important, and we're going to continue to innovate, and we fully expect to continue to drive cost out of the platform, whether that's larger cross-section stacks, achieving greater power density, whether that's just us building larger and more automated factories to take cost out, or indeed scale, giving us more buying power with our suppliers. So we don't think we're at an asymptote anywhere on cost down. So we're focused on continuing to improve efficiency, and I think the I&L work demonstrates that's certainly possible, as well as taking cost out, because, you know, it's not lost on anyone. This technology is still more expensive than PEM and alkaline, and we still have a job to do there from a first cost standpoint.
Thank you so much, Rick. And one thing I also sense in your response is that there's something similar like in PEM electrolysis. When you read in academic publications that the lifetime of PEM electrolysis was a lot lower than for alkaline electrolysis, and the only way to prove that it works is really putting it out in the world, right? Otherwise, you keep on with projects that are claiming it as a low lifetime. You just have to prove it. Now we are running close to the hour mark, so I would like to ask Andrea to put on the slides again. So for all the people who've watched from the audience, thank you so much for bearing with us. And this session will also be, all has been recorded as well. So it means that the recording will be available on our YouTube channel in about 2 days from now. And also we will write an article on the website. Now I also want to introduce the next project feature that we will do. It's next month, and we will focus on the HyEx project in Chile, where NEX tries to decarbonize its ammonia nitrate production in Chile using renewable ammonia production. So we will talk with Pablo Wallach from NEX, and also with Asuncion Borras from ENGIE. And the link is already in the description. So if you enjoyed this discussion and you would like to know what their project is about, please feel free to join this webinar as well. And that only leaves me with the last part of this webinar. I really like to thank Rick and Jakob for bearing with me for this entire hour. I hope you also had a good time discussing how solid oxides electrolysis could be coupled with an existing ammonia plant. So thank you.